In this lecture, we discuss the third and final factor that determines the length of the withdrawal time, the magnitude of the initial concentration of the marker residue in the target tissue. Of course, it makes sense intuitively that the higher the concentration, the longer the withdrawal time, but how does the dosing interval, and duration of treatment determine this concentration? The basic principle is that for every doubling of the initial tissue concentration relative to what the concentration would have been if the animal were given the label dose, the withdrawal time needs to be extended by one tissue half-life. But how do we know how a change in the dose is related to the doubling of the initial concentration in the target tissue? Well, for a single dose, this is quite easy. As it is the log to the base 2 of the ratio of the extra label dose, dose 2 in this case, to the label dose, dose 1. The calculation becomes a little more complex for a multi-dose regimen. First, we need to calculate the accumulation factor for each dosage regimen, which you notice is dependent on the plasma elimination rate constant, or K10, number of doses, N, and the dosing interval, tau. The doses are then weighted by their accumulation factor in the calculation of the ratio of the extra label to the label dose, and once again, the number of doublings is calculated as the log to the base 2 of the ratio. Notice that it is the plasma elimination rate constant, or K10, which is shorter than the terminal slope of the plasma concentration time curve, or tissue half-life, that is used in the calculation of the accumulation factor. And then to conclude, there's a simple formula that gets used to extend withdrawal times, provided we know by how much the initial tissue concentration has doubled, and we know the value of the tissue half-life.